about the crystal defect. In the last period, we learned vacancy defect. Now, the second one, self-interstitial defect in elemental solid, which is one of the stoichiometric point defect. What is definition? When some particle of a crystalline elemental solid occupy interstitial sites in the crystal structure, it is called the self-interstitial defect. Here two types. With two examples we can explain. When extra particle occupies an empty interstitial space in the crystal, it is the self-interstitial defect. Like in this case, the extra particle is observed here. Here extra particle, here again extra particle. So the density increases because volume remains the same. In second type, a particle gets shifted from its original lattice point and occupies an interstitial space, which is shown in this figure. Here vacancy is created and that vacancy is fulfilled here. This is the interstitial atom. In this case, no additional atom or ion or molecule, that is particle, is here. So density remains the same. Third type, Schottky defect. What is Schottky defect? In an ionic solid, equal number of cations and anions are missing from their regular position in the crystal lattice. Focus on these four words: equal number, cations and anions, and they are missing, which is observed in this figure. Here anion is missing, here cation is missing, therefore vacancy is created and mass and density naturally decreases. It is quite natural. What are the consequences of this Schottky defect? Electrical neutrality is preserved because here equal number of cation and anion are missing. Example, NaCl, KCl, etc. Fourth type is Frankel defect. When an ion of an ionic compound is missing from its regular site and occupies interstitial position between lattice point is called Frankel defect. Here you can observe vacancy of cation and that cation comes out here, cation at the interstitial site. The cations are usually smaller than anions. Therefore, cations occupy interstitial site. In example also, we show the cations occupying the interstitial site. Consequences. What is the effect? Number one, density remains unchanged. Second, crystal as a whole electrically neutral. Example, ZnS, AgCl, etc. Next is impurity defect. When foreign atom other than host atoms are present in the crystal lattice, it is called impurity defect. Impurity of foreign atom into the host atom. It is of two types, substitutional impurity and interstitial impurity defect. First, substitutional impurity defect. Foreign atoms are found at the lattice site in place of host atom. The standard example is of brass. What is brass? Brass is the alloy of copper and zinc. Observe this figure. In this case, the copper atoms are present in large number, which is host atom. And in between these copper atom, in place of that some copper atom, zinc atoms are present, which are the foreign atom. So, this is the example of substitutional impurity defect. Second example, vacancy through aliovalent impurity. Here, vacancies are created by the addition of impurity of aliovalent ion. What is aliovalent ion? Ions with oxidation state different from that of host ion. Means, for example, here if NaCl crystal is taken, sodium is the host ion, this cation, and here vacancy of sodium ion is created, and in place of that the other atom which having the oxidation state different from the host atom. Here sodium 1 oxidation state and SR atom having 2 plus oxidation state means different, and it occupy the position of sodium atom. This is called the aliovalent ion, ion with oxidation state different from that of the host ion. This is the another example. In order to maintain electrical neutrality, every Sr2 plus ion removes 2 sodium ions because oxidation state is different. In order to equalize, 2 sodium ions should be removed and Sr2 plus ion comes in place of sodium ion. Then second, interstitial impurity defect. The impurity atoms occupy interstitial spaces of crystal. Example, steel. What is steel? It is the alloy of iron plus carbon. The picture is like this. Here iron crystal is shown, and in between these spaces of iron atoms carbon is present. This gives rigidity to the iron. Thank you.